Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing Bedtime Astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky.
So I want you to imagine something for a second. Try to, picture looking at a photograph of a galaxy.
Okay.
Like a massive, swirling vortex of billions of stars, laced with those glowing veins of purple gas and thick, dark rivers of cosmic dust.
Right, something like a classic image beamed back from the James Webb Space Telescope.
Exactly. A stunning high-definition space image. Now, imagine a second photograph right next to it. And it looks completely identical.
Down to the pixel.
Right. The same complex spiral arms, the same chaotic star-forming regions, the exact same distribution of light and shadow. But there's a fundamental difference between these two images.
And it's a pretty massive difference.
Yeah, because one is a photograph of our actual universe, right? The product of 14 billion years of messy, chaotic, natural evolution.
Right.
But the other one is essentially a hallucination. It is a product of pure math, running on silicon chips in a basement somewhere here on Earth.
It's incredible to think about.
It really is. So what if we could build a universe inside a computer so mathematically perfect, so unfathomably detailed, that if you put those two images side by side, even professional PhD-holding astronomers couldn't tell you which one was real?
I mean, it sounds completely like science fiction, but it is the current very real frontier of computational astrophysics today.
Which is just wild to me.
It is. We are no longer just sketching rough approximations of how galaxies might form. We are synthesizing entire cosmoses from absolute scratch.
Wow.
Yeah, the boundary between observed physical reality and simulated digital reality is becoming, incredibly porous.
Okay, let's unpack this, because simulating an entire universe from the literal Big Bang all the way to the present day sounds like a task that would just melt any computer on Earth.
It definitely pushes the absolute limits of our current hardware.
I bet. Yet this massive decade-long scientific effort has just achieved exactly this. We are looking at a project that successfully simulated the evolution of galaxies by tracking the absolute smallest, microscopic specks of cosmic dust.
Down to the fundamental chemistry.
Right. And in doing so, they essentially rescued the entire standard model of the universe from being thrown in the scientific garbage bin.
They really did. It was a close call for a minute there.
Plus, they figured out a way for us to literally hear this virtual universe, which we will definitely get into.
Oh, the sonification stuff is fascinating. But the scope of the simulation itself is genuinely difficult to wrap your head around, even for the people actively working on it.
I can imagine.
But this endeavor really highlights a core philosophy of science, which is that knowledge is most valuable when it is rigorously applied to solve a crisis.
And there was definitely a crisis.
Oh, absolutely. For decades, astrophysicists have understood the broad theoretical strokes of how the universe expands.
The big picture stuff.
Right. But whenever they tried to actually build a digital model of it, the simulated galaxies always looked, they just looked wrong.
Like how wrong?
They were too clunky, the colors were off, the sizes just didn't match reality at all. The breakthrough here from this massive international initiative known as the COLIBRE project is that it proves something fundamental.
Which is?
If you want to get the massive billion light-year macro universe right, you have to perfect the microscopic physics first.
See, and that's the part that gets me. Because for the longest time, we weren't just struggling with the microphysics, right? We were actively, blatantly ignoring them.
Yeah, that's one way to put it.
I want to talk about this concept of the heat barrier in early simulations. Because when I first learned about this, it sounded completely absurd.
It is a bit counterintuitive until you understand the math behind it.
Right, but in all the older legacy simulations of the universe, scientists put a hard floor on the temperature of their virtual space, didn't they?
They did. A very strict temperature limit.
They artificially prevented the gas inside their virtual galaxies from cooling down below about 10,000 degrees Fahrenheit.
Which, just to put that into perspective for you, is significantly hotter than the surface of our sun.
Wait, really?
Oh, yeah. So imagine trying to code an entire virtual universe where literally nothing, no cloud of gas, no planetary nebula, no empty void is allowed to be cooler than a raging stellar surface.
It sounds like trying to study how a delicate French pastry is baked, but your oven only has one setting, and that setting is blowtorch.
That's a great way to describe it.
Like, how do you expect to bake a croissant, or in this case, forge a star, if every ingredient in your digital kitchen is instantly vaporized into superheated plasma?
Well, you don't. You simply don't. And that was the glaring flaw of late 20th and early 21st century cosmology.
It seems like such an obvious oversight.
It does, but to be fair to those early pioneers, it wasn't that astronomers didn't want their universes to be cold.
Okay, so why do it?
It was that modeling cold gas was computationally lethal to their machines.
Lethal how? Like, is cold gas harder to calculate than hot gas? I would assume hot things are more chaotic.
It's actually the exact opposite. Modeling cold gas is exponentially harder.
Really?
Yeah. When we talk about gas moving through space, we are really talking about hydrodynamics. In astrophysics, we treat these massive clouds of hydrogen and helium like a fluid.
Like water flowing in a river.
Sort of, yeah. We have to calculate their pressure, their viscosity, how they flow, and crucially, how they react to the gravitational pull of dark matter.
Okay, that makes sense.
Now, when gas is kept artificially hot at 10,000 degrees, it has a lot of thermal pressure. It's smooth, it expands outward evenly.
It's predictable.
Exactly. The math to track a smooth, expanding balloon of hot fluid is relatively straightforward for a supercomputer. It can handle that easily. But what happens to a gas when you cool it down?
It condenses, right? It shrinks and gets thicker.
Exactly. It loses all that outward thermal pressure. So gravity suddenly takes over and the gas starts clumping together into microscopic, incredibly dense pockets.
Oh, I see.
It becomes chaotic and highly nonlinear. To calculate the hydrodynamics of cold, clumpy gas, your computer grid needs a massive, massive increase in resolution.
Because there's more stuff happening in a smaller area.
Right. You have to track millions of tiny, independent, highly dense collapsing nodes instead of just one big, smooth cloud.
So the computers just couldn't handle the math.
Exactly. If older supercomputers tried to let the gas drop below 10,000 degrees, the simulation would essentially choke on the math and crash. The algorithm simply couldn't handle the resolution required to track all those tiny clumps.
But the physical reality we actually live in completely relies on that cold gas.
It relies entirely on it.
Right. Like, if the real universe couldn't cool down, the gas would never clump, stars would never form, and you and I wouldn't be sitting here talking about it.
No, we wouldn't. And this is the grand irony of early cosmological simulations. Stars only form in molecular clouds that are incredibly cold. We are talking just a few degrees above absolute zero.
Wow, that cold.
Yes. At those freezing temperatures, the gas has virtually zero thermal pressure pushing outward.
So gravity just completely takes over.
Precisely. Without that outward push, the inward pull of gravity finally wins the tug-of-war. The cold gas collapses in on itself, becoming denser and denser until the pressure at the core is so extreme that it ignites nuclear fusion.
And boom, a star is born.
Exactly. But if your virtual universe is artificially locked at 10,000 degrees, the gas is just moving too fast. It has too much kinetic energy.
So it just zips right past itself.
Right. Gravity can never grab onto it long enough to forge a star. What's fascinating here is how this forced scientists to reevaluate their entire approach.
So wait, if the physics in those older simulations physically prevented stars from forming, like mathematically made it impossible, how do they get galaxies? Do they just hack the code?
Yeah, essentially. They used a conceptual band-aid called subgrid physics.
Subgrid physics. That sounds like a polite way of saying we made it up.
Well, kind of. Because the computer grid couldn't zoom in far enough to simulate actual cooling and collapsing, they wrote a statistical workaround, an arbitrary rule.
How did that work?
The code basically said, hey, if a pocket of hot gas reaches a certain density threshold, just pretend it magically cooled down, delete the gas, and spawn a star particle in its place.
Wow. So they were just spawning in stars like items in a video game based on a rough guess.
Exactly. Just dropping them in when the math looked close enough.
That means for years, an enormous chunk of our understanding of galaxy evolution was built on a giant blind spot.
A huge blind spot.
We were trying to map the cosmos while completely ignoring the actual environment where galaxies build themselves.
Right. It was an educated guess, but you can only rely on statistical band-aids for so long before your virtual universe diverges so far from reality that it just stops being scientifically useful.
Right. Eventually, the cracks are going to show.
Absolutely. Eventually, you have to find a way to break that heat barrier and let the virtual cosmos freeze.
And breaking that barrier wasn't just a matter of like waiting for Apple or IBM to build a faster microchip.
Right.
You actually had to write new physics into the simulation.
Yes, entirely new physics.
And this is where the COLIBRE project completely changes the game. To cool the universe down, they had to introduce two highly specific ingredients that had never been successfully modeled on this scale before, right?
Right.
Molecular hydrogen and cosmic dust.
Yes, and let me stop you there because it is vital to understand why those two things go hand in hand. You cannot have cold molecular hydrogen in space without cosmic dust.
Right.
Dust is the great enabler of the universe.
Which is such a wild paradigm shift. Because normally if you ask an amateur astronomer about dust, they'll just groan.
Oh, they hate it.
Right. Dust is the annoying haze that blocks the light from the beautiful glowing nebulae behind it. It's an obstacle. But here, dust is essentially the VIP of the universe. So what does this all mean? Why is it so important?
Well, because the vacuum of space is an incredibly hostile place to build a molecule. The primary ingredient for a star is molecular hydrogen, which is just two hydrogen atoms bonded together.
Okay, simple enough.
But in the vast, empty expanse of an early galaxy, trying to get two single hydrogen atoms to bump into each other and bond is nearly impossible.
Because space is just too big.
The space is too vast, the atoms are moving too fast, and if they do happen to collide, they usually just bounce off each other.
Why do they bounce?
Because they have nowhere to dump their excess kinetic energy. They hit, and the energy just pushes them right back apart.
It's like trying to get two pieces of Velcro to stick together by firing them out of cannons at each other across an empty football stadium.
That is a brilliant way to visualize it. They're just going to ricochet.
Exactly.
They need a mediator, they need a surface to slow them down, and this is exactly where a microscopic grain of cosmic dust comes in.
Okay.
Now, when we say dust in astrophysics, we aren't talking about the dust bunnies under your couch.
Right. It's not skin cells and lint.
No. We are talking about microscopic, solid particles of silicates or carbon, essentially tiny grains of sand or soot forged in the dying breaths of older stars.
Okay, so stellar soot.
Yes. And these solid grains act as a catalytic docking station.
So a single hydrogen atom is flying through the stadium, and instead of hitting another atom, it crashes into this giant, well, relatively speaking, grain of soot.
Yes. It hits the dust grain and actually sticks to its surface. The dust grain absorbs the atom's kinetic energy, acting as a thermal sink.
Oh, so it bleeds off the speed.
Exactly. Then another hydrogen atom hits that exact same dust grain. It wanders on the solid surface until it finds the first atom.
And because they're both slowed down?
They bond. They form molecular hydrogen and then drift off the dust grain together into space.
So the dust is literally acting like a cosmic anvil where the fuel for stars is hammered together.
It is the factory floor of star formation. But its job doesn't end there.
There's more.
Oh, yeah. Once that molecular hydrogen forms, it is incredibly fragile. A galaxy is a violent place, flooded with harsh, destructive ultraviolet radiation pouring out of young, hot stars.
So it's basically a hostile environment for these new molecules.
Very hostile. If that UV radiation hits our newly formed molecular hydrogen, it excites the molecule, heats it up, and literally blasts it apart.
Oh, yeah.
It destroys the fuel supply for any future stars.
It just sterilizes the whole region.
Precisely. Unless the dust steps in again.
The VIP returns.
Exactly. Cosmic dust is incredibly effective at absorbing ultraviolet light. It blankets these cold molecular clouds, acting as a physical shield.
So it takes the hit.
Right. The UV radiation hits the dust on the outside of the cloud, while the fragile hydrogen gas, safely nestled deep inside, remains freezing cold.
It's like the universe's own SPF 10,000 sunscreen.
That's a perfect analogy.
The dust takes the hit, so the baby stars can incubate in the dark, cold center. And the COLIBRE project was the first time anyone managed to mathematically track these microscopic soot grains, like their chemical reactions and their shielding effects, across an entire simulated universe.
On this massive of a scale, yes.
That is mind-blowing.
And what's fascinating here is that introducing dust didn't just fix the physics, it completely revolutionized the visuals of the simulation, too.
How so?
Well, think about it. If the dust is absorbing all that intense ultraviolet starlight, that energy can't just vanish. The laws of thermodynamics dictate it has to go somewhere.
Right. Energy cannot be created or destroyed, so the dust heats up and starts glowing in a different wavelength.
Exactly.
It re-emits the energy as infrared light.
Exactly. And that completely alters how a simulated galaxy appears when we look at it.
Yeah.
For the first time, researchers were creating virtual galaxies that didn't just have the right mass or gravity.
They actually looked real.
They actually look like the galaxies we observe through infrared telescopes.
I was actually looking at the visual outputs the COLIBRE team published. They showed a rendering of a virtual disk galaxy, structurally very similar to our own Milky Way, right? From two different perspectives.
Yes, the face-on and edge-on views.
Right. When you look at it face-on, from the top down, it is this brilliant, glowing spiral of starlight. But when they rotate the simulation and show it to you edge-on from the side, the starlight is suddenly choked out by this dense, dark, suffocating band of dust slicing right through the galactic equator.
It's a dramatic visual shift.
It really is. It perfectly mimics the real optical telescope images we get of edge-on galaxies.
And that visual fidelity is what makes this a monumental achievement. We are no longer limited to comparing abstract graphs of theoretical mass,
We're comparing actual pictures.
Exactly. We can take a real observed image from a space telescope, put it next to a simulated image from COLIBRE, run both images through the exact same analytical software, and test if they match. We can measure the exact obscuration of light.
But hold on. The sheer computational brute force required to do that is... I can't even process it.
It's staggering.
You are asking a computer to track microscopic grains of soot, calculate the fluid dynamics of freezing gas, apply the gravitational pull of billions of dark matter halos, and compute the radiation physics of starlight all across a volume of space that spans hundreds of millions of light years.
It's a lot of math.
What kind of machine is actually capable of calculating that matrix?
Well, it requires an architecture that is almost as complex as the simulation itself. The physical engine running this was the COSMA8 supercomputer, which is hosted by the Dirac National Facility at Durham University in the UK.
Oh.
But hardware alone isn't enough. You can have the absolute fastest supercomputer in the world, and if your code is inefficient, it will still crash when trying to simulate a freezing galaxy.
Right, because of that resolution bottleneck we talked about earlier.
Exactly. The real hero here is the software code they wrote, which is called Swift.
Swift. Okay, so how does Swift handle the math differently than the older codes that used to crash when the gas got cold?
Older cosmological codes usually operated on rigid time steps.
What does that mean?
It means the computer would calculate the gravity, temperature, and velocity of every single particle in the entire universe, move the simulation forward by one tick of the cosmic clock, and then recalculate everything all over again.
Oh, wow. So which means the computer has to wait for the absolute slowest, most complicated calculation to finish before the whole universe is allowed to move forward 1 second.
Exactly. It creates massive processing bottlenecks.
Like a traffic jam.
Very much like a traffic jam. Swift entirely abandoned that model. It uses task-based asynchronous parallelism.
Meaning?
It breaks the universe down into millions of independent tasks. If a cold, dense cloud of gas in one corner of the simulation is highly chaotic and needs to be calculated in incredibly tiny fractions of a second, the processor handles that locally.
Without making the rest of the universe wait.
Right. Without forcing a quiet, empty void on the other side of the virtual universe to slow down and wait for it, the code dynamically shifts computational power exactly where it is needed, the millisecond it is needed.
So it's essentially a self-optimizing universe.
It is.
And even with that hyper-efficient code, the scale of the simulation they ran is just staggering. I want you, the listener, to really internalize these numbers for a second. The largest simulation in the COLIBRE suite required 72 million CPU hours to complete.
That's 72 million hours of continuous processing.
72 million. If you somehow manage to install this Swift code onto a top-of-the-line 2026 gaming laptop and you hit run, your computer would have to sit there processing at 100% maximum capacity 24 hours a day for over 8,000 years before it finished calculating what calls an A8 did.
And that 72 million hours produced a volume of space that is unprecedented in its resolution. They built multiple simulated universes, but their largest box has a side length of 400 co-moving megaparsecs.
Now wait, co-moving megaparsecs. A megaparsec is about 3.26 million light years. But what does co-moving mean? Why not just say a billion light years?
Well, because the universe is expanding.
Right.
If you measure the distance between two galaxies today and then wait a billion years, the distance between them will be larger, even if the galaxies themselves haven't actually traveled through space.
The space itself stretched.
Exactly. Space itself stretched. Co-moving is a coordinate system that expands along with the universe.
How does that work?
It's like drawing two dots on a deflated balloon. As you blow the balloon up, the dots get further apart, but their co-moving distance, their relative position on the rubber, stays exactly the same.
Oh, that's a great visual.
Using co-moving megaparsecs allows the simulation to track the evolution of matter without the math getting distorted by the expansion of space itself.
That is deeply counterintuitive,
Right.
but it makes perfect sense for a simulation tracking 14 billion years of history.
It's a
So this massive box, over 1 billion light years across, is just relentlessly churning through these equations. And there's a quote about this process from Carlos Frank. He's the Ogden Professor of Fundamental Physics and a core member of this team that I found deeply profound.
Yeah, he summed it up perfectly.
He pointed out that they didn't paint these galaxies. They didn't tell the computer, hey, put a spiral galaxy over here and an elliptical galaxy over there.
No hard coding shapes.
They literally just inputted the raw fundamental equations of gravity, thermodynamics, and chemistry, hit play on the Big Bang, and the galaxies built themselves.
It is the ultimate testament to the emergent complexity of physics.
It really is.
When you finally provide the equations with sufficient resolution, when you respect the dust and the cold gas reality naturally emerges from the math.
Wow.
The simulated galaxy spontaneously grew to have the exact same masses, the exact same colors, and the exact same chemical compositions, what astronomers call metallicity, as the real galaxies we observe.
Let's actually define metallicity real quick, because astronomers use that word very differently than normal people do.
That's true, they do.
If I say metal, people think of iron or aluminum.
Right, but to an astrophysicist, the periodic table is incredibly simple. There is hydrogen, there is helium, and literally every other element in the universe, carbon, oxygen, nitrogen, iron, is considered a metal.
So oxygen is a metal.
In astronomy, yes. These heavy metals are forged in the nuclear furnaces of early stars and then blasted out into space when those stars die in supernovae.
And then that seeds the next generation.
Exactly. That metal-rich dust then seeds the next generation of stars. COLIBRE tracked that exact chemical enrichment process over billions of years.
Okay, so building this ultimate virtual laboratory is an absolute marvel of human engineering. But the critical question is, what do we do with it?
Right, application is key.
Did spending 72 million CPU hours actually solve any real-world problems? Because right around the time this supercomputer was redlining, the actual astronomy community was undergoing a massive existential crisis, weren't they?
They were in an absolute panic, and that panic was entirely courtesy of the James Webb Space Telescope.
I remember this. When JWST finally launched and sent back its first deep-field images, it pointed its incredibly sensitive infrared sensors at the very edge of the observable universe, right?
Yes.
Peering into the first few 100 million years right after the Big Bang. Because, light takes time to travel, so looking far away is literally looking back in time.
Yes, it's a time machine.
Oh.
And the established standard model of cosmology, which is called the lambda CDM model, incorporating dark energy and cold dark matter, had very specific predictions for what the universe should look like in that early era.
What were those predictions?
The model predicted that early galaxies should be small, chaotic, ragged little clumps of stars, slowly building themselves up over billions of years.
Like stepping stones.
Exactly. But when JWST looked back at the dawn of time, it didn't find ragged little clumps.
No.
No, it found massive, incredibly bright, fully formed galaxies.
They were way too big, way too fast. I remember the headlines were everywhere, JWST breaks the universe, the Big Bang Theory is wrong.
It was a very dramatic few months.
It was as if an archaeologist dug down into a Bronze Age settlement and found a fully functional nuclear reactor. It violated the established timeline of reality. You could feel the tension in the scientific community.
People were genuinely terrified.
Right. People were terrified that the fundamental blueprint of cosmology, which thousands of scientists had dedicated their entire lives to, was fundamentally broken.
The dread was very real. If the standard model was wrong, it meant we basically understood nothing about dark matter or dark energy.
We'd have to start from scratch.
Essentially,
Yeah.
yes. And this is exactly where the COLIBRE project proved its immense, undeniable value.
Because they could test it.
Right. Dr. Evgeny Chaikin, the lead author of several of the major COLIBRE papers, used this brand new virtual universe to test the crisis. The team essentially acted as virtual astronomers. They aimed a digital version of the James Webb Telescope into the deep past of their simulated universe to see what they would find.
And here's where it gets really interesting. The standard model wasn't broken at all, was it? We just had terrible rendering software.
That is exactly what they proved. When Dr. Chaikin ran the virtual observation, the COLIBRE simulation effortlessly produced those exact same massive, hyper-bright early galaxies that the real JWST was seeing.
Wow.
They naturally emerged within the strict confines of the standard lambda CDM model.
Wait, if the standard model allowed for these massive galaxies the whole time, why did our previous predictions say they shouldn't exist?
Because the previous predictions were based on legacy simulations that couldn't model cold gas and dust.
Oh, the 10,000-degree floor.
Remember that heat barrier? If your simulated universe artificially prevents gas from cooling, you are artificially suppressing the rate at which stars can form.
So you're stunting their growth in the simulation.
Precisely. Your virtual early universe will look sluggish and dim, not because the fundamental laws of cosmology dictate it, but because your computer code is stifling the chemistry.
So the moment COLIBRE added the microscopic dust and let the gas freeze, the early galaxies suddenly had the fuel they needed to ignite massive firestorms of rapid star formation, matching the JWST data perfectly.
Yes. And furthermore, COLIBRE successfully modeled the intense, explosive outflows of energy driven by those early stars and supermassive black holes.
It all just clicked into place.
It proved that the universe didn't need entirely new physics. It just needed us to model the messy microscopic chemistry correctly. If we connect this to the bigger picture, it shows the standard cosmological model is perfectly sound.
I can just imagine the collective exhale across university physics departments worldwide.
Oh, the relief was palpable.
It's a profound lesson. When a new, shiny piece of technology like JWST gives you observations that contradict your life's work, the immediate reaction shouldn't be to throw out the physics textbook.
Right.
Sometimes the overarching theory is perfectly fine, but your ability to model its intricate, emergent behaviors is just lacking.
It is a massive victory for the standard model. But here the universe still has secrets that even 72 million CPU hours couldn't decipher.
Oh.
Because as brilliantly as Kala solved the crisis of the massive early galaxies, it ran into an absolute brick wall when it came to another of JWST's most bizarre discoveries.
You're talking about the phenomena that astrophysicists are currently referring to as the ghosts in the machine?
Yes.
The little red dots?
And little red dots. It is such an unassuming, cute name for what are essentially the most terrifying cosmic monsters in the early universe.
What exactly are they?
Well, JWST discovered these highly compact, heavily obscured, intensely red sources of light buried deep in the first billion years of the cosmos. The current consensus is that we're looking at the foundational seeds of supermassive black holes.
Right, because we know that almost every large galaxy today, including our Milky Way, has a supermassive black hole at its dead center.
We're orbiting one right now.
Exactly. Some of them are billions of times the mass of our sun. But the mystery has always been,
Yeah.
how did they get so monstrously huge so early in the universe's timeline?
It's a massive timing problem.
There simply wasn't enough time for a normal-sized black hole to slowly eat enough gas to get that big.
And this is where the grand, perfect COLIBRE simulation basically throws its hands in the air and gives up.
Really?
The simulation cannot mathematically predict or naturally form these early supermassive black hole seeds.
This shocked me. Wait, so after a decade of international collaboration, writing millions of lines of the most advanced physics code ever conceived, and letting a supercomputer chew on it for 8,000 computational years, the scientists still have to manually plant black holes in the simulation like they're planting trees in a digital garden.
We do. We literally have to do that. The simulation assumes the black hole seeds already exist at a certain mass and manually injects them into the centers of the virtual early galaxies.
That feels like a cheat code. Why can we perfectly simulate the fluid dynamics of a coal dust cloud condensing into a star, but we can't simulate the genesis of a black hole?
Because the birth of these specific supermassive seeds requires physics that humanity does not fully understand yet.
We just don't have the equations.
Right. Simulating a star is incredibly complex, but we know the rules of thermodynamics and nuclear fusion. But the origin of these little red dots is a theoretical frontier.
So what are the theories?
Well, some cosmologists hypothesize that they form from the direct collapse of massive, pristine, metal-free gas clouds.
Meaning the gas cloud gets so heavy, it just entirely skips the process of becoming a star and immediately crushes itself into a black hole singularity.
Yes, just an instant massive collapse. Other theories suggest they are formed from runaway chain reaction collisions inside unbelievably dense early star clusters.
Like a cosmic demolition derby.
Essentially, yes. But the gravity and density involved in these events approached the singularity, the point where our current mathematical equations for general relativity literally break down and output infinities.
The math just stops working.
Exactly. To model those events natively, without manual human intervention, will require grid resolutions that make COLIBRE look primitive and entirely new equations of quantum gravity written into the code.
It is a phenomenal reality check. The simulation is a flawless mirror of nature right up until the exact millimeter where human knowledge itself hits a cliff.
It is a very stark boundary.
But the team isn't just packing up their bags, are they?
Not at all. While the foundational COLIBRE runs were completed recently, some of the absolute highest resolution simulations are currently running right now, eating up more processor hours, trying to push that boundary further.
But the work continues.
Oh, absolutely. And the data they've already generated is so vast, petabytes upon petabytes of information, that it will take the global scientific community a decade just to fully read and analyze it.
And while the supercomputers grind away at the next era of frontier physics, the scientists have developed a radical, entirely new way for humans to experience the petabytes of data we already have.
This might be my favorite part.
Which brings us to the final and visually, or rather sensorially, most fascinating aspect of this endeavor. We aren't just looking at the virtual universe anymore. We are hearing it.
This is a truly innovative approach led by Dr. James Trayford at the University of Portsmouth.
Right.
He was the lead developer of COLIBRE's complex dust model, but he also spearheaded the creation of what they call sonified videos. They are creating a multi-sensory cosmos.
Normally, astrophysics is entirely visual. We look at scatter plots, line graphs, and beautiful false color renderings of nebulae. But Dr. Trayford took this dense, mathematically terrifying digital universe and applied sonification, essentially encoding physical astronomical data into sound.
And let's be clear about what sonification is not. They aren't just overlaying a pretty Beethoven symphony onto a video of a galaxy spinning.
It's not just a soundtrack.
No. They are mapping highly specific physical properties of the simulated universe directly to acoustic parameters.
Can you give an example?
Sure. For instance, the velocity of stars orbiting the galactic center might be mapped to the pitch of the sound. The rate at which new stars are forming, the star formation rate, might be mapped to rhythm or volume.
So instead of trying to read a chaotic line graph, you could listen to a galaxy, and the pitch would literally rise and fall as the galaxy's rotation speeds up or slows down.
Precisely. Or imagine listening to the sonified data of a galaxy's cold gas reserves.
Okay, what would that sound like?
You hear a steady, low-frequency hum representing the molecular hydrogen.
The fuel.
Right. Then suddenly, the hum is violently interrupted by sharp, staccato, high-pitched rhythmic bursts.
What's that?
That represents the thermal shock waves of supernovae exploding as a burst of star formation occurs.
Wow. It's like acoustic diagnostics. If you think about it, human beings do this all the time in everyday life.
We do.
Yeah. If you are sitting in traffic and your car's engine suddenly starts making a subtle rhythmic ticking noise, your brain detects that anomaly instantly, often long before a warning light flashes on your dashboard.
That is exactly the cognitive mechanism Dr. Trayford is tapping into. This raises an important question about how we process data. Human hearing evolved to be extraordinarily sensitive to patterns, rhythms, and subtle changes in frequency.
Much more so than our eyes sometimes.
Exactly. Our auditory processing can often pick out a single anomalous data point in a chaotic environment much faster than our visual processing can spot a rogue dot on a crowded scatter plot.
So if a simulated galaxy undergoes a violent merger with another galaxy, the visual data on a screen might just look like a messy, blindingly bright blob of light.
Hard to decipher.
Right. But the sonified data would hit your ears as a distinct, chaotic acoustic crash, followed by a settling resonance as the two gravitational fields finally merge and stabilize.
By making the data multisensory, they are effectively training human intuition.
That is so cool.
Science isn't just the cold collection of numbers, it is the human comprehension of those numbers. By allowing researchers to sit in a lab with headphones on and interactively fly through the COLIBRE universe, feeling the rhythm of star formation and hearing the pitch of dark matter gravity, they are building a deeper, almost subconscious instinct for how galaxies evolve.
It bridges the gap between the incredibly abstract math of an expanding universe and the physical sensory experience of the human body.
It makes the math tangible.
It really does. It is an absolutely wild journey when you zoom out and look at the sheer scope of what we've explored today.
It is a testament to how far we have come in such a short amount of time.
We started with crude legacy simulations that were literally too hot to handle, restricted by an artificial 10,000-degree floor that completely blinded us to the true nature of star formation.
We couldn't see the forest for the fire, basically.
Right. Then scientists painstakingly cracked the mathematical code of cosmic dust, proving that the tiniest, most microscopic specks of soot are the ultimate architects and thermal protectors of the largest galaxies in existence.
The COSMOS VIPs.
The VIPs. We unleashed the unfathomable brute force of the COSM A8 supercomputer, burning through 72 million asynchronous CPU hours to synthesize a one-to-one scale universe out of pure fluid dynamics and gravity.
A digital triumph.
And in doing so, we essentially saved the standard model of the cosmos from the terrifying, reality-bending early observations of the James Webb Space Telescope.
And yet we remain profoundly humbled by the limitations of our own knowledge, staring into the abyss of the little red dots, waiting for the next generation of physics to explain how the universe's ultimate monsters are born.
It really is a story of human audacity. And I want to leave you with one final mind-bending thought to ponder as you go about the rest of your day. We just spent this entire time dissecting how human beings, right now, in the 2020s, have built computers capable of generating a digital universe so physically accurate, so perfectly rendered, that even our best professional astronomers cannot distinguish its virtual galaxies from reality.
That is a fact.
If we could achieve that level of simulation today, what happens in a century? What happens after 1,000 years of computational advancement?
It's almost scary to think about.
Is it entirely possible that the grand, beautiful, chaotic universe you and I are currently observing, the stars, the dust, the massive early galaxies we see through our telescopes, is actually just a highly detailed, perfect simulation running on someone else's supercomputer?
The ultimate simulation theory.
Exactly. Keep looking up at the stars, everyone, and maybe, if you listen closely enough, you can hear the hum of the processor.